Welcome to this explainer. If you really think about it, from the smartphone sitting in your pocket right now, to the EV in your driveway, or even the medical implants literally saving lives, our modern civilization is completely bound by the limits of the materials we use. But today, we're exploring an absolute revolution that's rewriting those limits from the atomic level up. Okay, let's just quickly breeze through our roadmap for this explainer. We're going to start with the trial and error problem, then we'll enter materials informatics. After that, we'll look at smart and sustainable materials, powering a clean future, the nanoscale revolution, and finally the autonomous future. Section 1. The trial and error problem. So for centuries, discovering a new material meant years of grueling laboratory trial and error. We're talking about scientists blowing through massive amounts of grant money, testing thousands of doomed combinations in a lab just to find one that kind of works. And honestly, that old way, it's just way too slow for today's massive energy and healthcare crises. Which brings us to a really provocative question. What if materials could design themselves? Think about the stark contrast here. The traditional method meant literally years of work, crazy expensive overheads, and severely limited testing through physical trial and error. But the AI-based method? It completely flips the script. We are now living in a reality of days or weeks, relying on massive virtual screening. It's this incredibly cost-efficient, data-driven approach where we can computationally estimate how a material will behave way before anyone even touches a beaker in a lab.
Section 2. Enter Materials Informatics.
So, materials informatics. This is where the hard sciences of chemistry and physics totally collide with computer science, data science, and the artificial intelligence. The main goal here is pretty mind-blowing. Instead of relying on physical guesswork, we let machine learning algorithms analyze these huge data sets to predict a material's properties computationally, long before it's actually synthesized. These AI models feed on vast datasets of specific properties, things like density, conductivity, hardness, thermal stability, and elasticity. Being able to computationally predict something highly specific, like saying, okay, we need an exact 1.5 electron-volt band gap for this new semiconductor, that saves immense amounts of time and money. It essentially eliminates thousands of dead-end physical experiments right out of the gate. And all that data processing leads us to high-throughput screening. You can think of this like an ultra-fast digital sorting hat for chemistry. Instead of testing candidates one by one in a physical lab, the AI rapidly evaluates thousands or even millions of material candidates virtually. It ranks them instantly based on performance, stability, and cost, which ensures that researchers only focus their time and resources on the absolute best candidates. Section 3. Smart and sustainable materials. AI is actively helping us design what we call smart materials. These are materials that dynamically respond to external stimuli: temperature, light, electric fields, or pressure. We're talking about shape memory alloys that you can crush, but they automatically snap back to their original shape. Or self-healing materials that literally repair their own structural damage. And responsive polymers that actively change their properties the second environmental conditions shift. It's almost like science fiction. Speaking of polymers, AI is totally overhauling how we design the everyday plastics, fibers, and coatings we rely on. Machine learning algorithms predict mechanical properties like strength, flexibility, and chemical resistance. And this is absolutely crucial because it allows us to create truly sustainable, biodegradable alternatives to traditional packaging. By using AI to identify polymers that perform great but break down harmlessly, we suddenly have a massive new weapon against global pollution. Section 4. Powering a clean future. Look, our entire global shift toward electric vehicles and renewable energy grids, it depends entirely on batteries. We desperately need higher energy density, faster charging, and better safety. Well, AI accelerates all of this by predicting the capacity, conductivity, and long-term degradation of vital battery components, like cathodes, anodes, and electrolytes. That means faster screening, massively reduced manufacturing costs, and ultimately saying goodbye to range anxiety in your EV for sure. And it's the exact same story for solar cell materials. Boosting solar efficiency is literally one of the greatest scientific challenges we face today. AI is speeding up the development of everything from traditional silicon-based cells to flexible organic photovoltaics to these emerging crazy efficient materials called perovskites. By predicting light absorption and electronic properties with hyper-accuracy, machine learning is helping us capture the sun's energy cheaper and faster than ever before. Section 5. The nanoscale revolution.
When we zoom way down to the incredible tiny nanoscale, dealing with materials just 1 to 100 nanometers in size, the standard rules of physics just kind of warp. At this scale, materials show dramatically enhanced reactivity, huge surface areas, and totally unique optical traits. But predicting behavior, complex surface interactions, or even toxicity at this scale, it's mathematically staggering. AI is basically mandatory here because traditional trial and error simply can't handle the complexity.
Two awesome examples of AI optimization here are graphene and quantum dots. Machine learning is helping us perfect graphene, which is famous for its incredible strength, flexibility, and conductivity. It's actively revolutionizing electronics right now. At the same time, AI predicts the exact emission wavelengths, stability, and synthesis conditions for quantum dots. Those are the nanoscale semiconductors giving your modern displays and medical imaging their vibrant, incredibly precise colors.
AI is also a complete game changer for catalyst discovery. Catalysts are essential because they accelerate chemical reactions without being consumed themselves. Machine learning rapidly predicts reaction performance and surface properties to design catalysts that have high activity and high selectivity. And this is exactly what's driving the optimization of petrochemical refining, the leap forward in green chemistry, and the clean production of hydrogen fuel.
Section 6. The autonomous future. So the big takeaway here is that we aren't just speeding up human chemistry, we're fundamentally changing the laboratory itself. A huge part of this autonomous future relies on digital twins. A digital twin is a virtual replica of a real material or manufacturing system, and it's continuously updated by AI using real-world data. Think of it like a highly advanced virtual test dummy. Scientists can predict performance, optimize manufacturing, and figure out exactly where something will fail entirely in a simulation. That drastically cuts down physical risk and makes decision-making so much sharper. Which leads us to the holy grail, a totally closed-loop workflow of autonomous materials discovery. Check this out. Step 1. The AI proposes a new material. Step 2. Robotic systems physically synthesize the sample. Step 3. Measurements are automatically collected. Step 4. The AI analyzes those real-world results. And Step 5. New, optimized candidates are instantly generated. It's just a continuous, self-improving engine of innovation that runs with practically zero human workload. Now, to be completely fair and objective, it's not all perfect yet. There are real challenges facing the field today. Researchers are fighting constant battles with data availability and quality because, hey, if your data set is incomplete or inaccurate, the AI's reliability completely tanks. Also, real-world materials have highly complex behaviors that are incredibly hard to perfectly simulate. And then there's interpretability. The black box nature of AI means it might give us the perfect answer, but understanding exactly how it got there, that's still a major hurdle. Which brings us to a really fascinating, provocative thought to end on. In a world of fully autonomous labs, robotic synthesis, and instant AI predictions, what exactly is the future role of the human chemist? If the machines are handling all the trial and error, the scientists of tomorrow won't just be standing at a bench mixing liquids. They're going to need to master robotics, high-performance computing, and deep learning just to survive and thrive. It really seems like the future of understanding our physical world relies entirely on how well we can speak the language of the digital one. Thanks for joining me on this explainer, and keep exploring.